So as I mentioned in the last screencast, this was a bit of a poorer break than really what I wanted. I really wanted all the ether stuff to go together, but it didn't, and so here we are. So our ability to design a synthesis is limited by the reactions we know. A synthesis can also present challenges when functional groups that appear in the compound we have available are not the functional groups required to carry out the necessary synthetic steps. So in many cases, we can often make use of functional group transformations to help us. So for example, here's the problem. We want to design this ether here, but when we go to the stockroom, all we have are alcohols, right? So we can use any alcohol to design this. To use a Williamson ether synthesis, we could use an alkyl halide and an alkoxide ion shown here. The problem is neither reagent's an alcohol. So our task now is to determine how the alkyl halide and the alkoxide ion can be produced from alcohols to then react so that they can produce the product that we're looking for or our target. So then we can turn to functional group transformations. To produce the alkyl halide from the corresponding alcohol, consider the functional group transformation shown here, where we have an alcohol, we have an acid, and now we have an alkyl halide. Specifically, we could treat the benzyl alcohol here with a strong acid like HCl, and we could produce this as the alkyl halide. To produce the alkoxide anion from alcohol, we can take advantage of the strategy presented in 9.3b for generating strong nucleophiles, where you carry out a deprotonation using sodium hydride. And so this is a pretty powerful base. And so basically it just goes through proton transfer, right? And so now we have an alkoxide anion. Okay, so knowing how to produce the reactants necessary for the desired Williamson synthesis, we can then present the whole synthesis together this way, where we take the alcohol here, we treat it with HCl, there's our alkyl halide, we have our alcohol here, we treat it with a strong base like sodium hydride. Now we have our alkoxide anion. These can react in a Williamson ether synthesis, and we've synthesized our final product here. So our discussion in the ether section was really specific, dealing with the synthesis of only one type of compound, ethers, and considering just one type of restriction, which the starting materials have to be an alcohol. But the takeaway lesson from this does apply really broadly to your education. Functional group transformations are not only useful in producing functional groups that appear in the target, but can also be useful to produce functional groups that allow a subsequent synthetic step to occur. Our ability to design a practical synthesis will improve with each additional functional group transformation that we learn. And so for this reason, we are going to devote the rest of this chapter to introducing more functional group transformations that are useful in synthesis. So buckle up. For the rest of the chapter, what we're looking at is how can we change functional groups. In section 10.4, we saw just a second ago how useful it can be to convert an alcohol into an alkyl halide, such as an alkyl chloride or an alkyl bromide. That conversion is particularly desirable because the alcohol itself is a really poor leaving group for nucleophilic substitution elimination reactions, whereas bromide and chloride are quite good leaving groups. Both bromine and chlorine are much larger than oxygen and can stabilize that negative charge better, making them just better leaving groups altogether. So one way to carry out the conversion, which we saw previously, is to treat an alcohol with concentrated hydrochloric acid or hydrobromic acid. And so in the example that we see here, 1-butanol is converted to 1-bromobutane when it's treated with concentrated hydrobromic acid. Now, let's look at the mechanism for this. Under acidic conditions, which is, a hydrobromic acid is a strong acid, so these are considered acidic conditions. the poor leaving group of the alcohol is converted to a very good leaving group through a proton transfer reaction. Right? And so what happens here is these electrons come and grab that proton. Those electrons go back on the bromine. When this happens, we have our protonated alcohol, right? And that forms water, and we know that water is a super good leaving group. Now, the bromine that's generated can then come in and attack the electrons on that bromine, can attack the carbon next to the leaving group, right? Pushing off that water in a SN2 reaction. So this undergoes an SN2 reaction. And now, 1, 2, 3, 4, we have bromine there. So the substrate, a few things to kind of notice here. The substrate's primary. So the displacement that takes place by an SN2 is very favorable. Obviously, we couldn't do that if we had a tertiary substrate. Now, one of the things that you're going to notice in organic chemistry is there are always exceptions. And obviously, this looks beautiful. It looks like it's going to work. But you can still get a variety of problems with this type of reaction. For example, the conditions are really strongly acidic. So if the molecule has other functional groups, the substrate molecule, that are sensitive to acidic conditions, they could react, okay? If the substrate were to be secondary or tertiary, then these reaction conditions would favor both SN1 and E1 mechanisms, and in that case, the competing E1 would reduce the yield of the SN1 product, right? So those are some problems there. Let's talk a little more about the SN1, right? Also, so if we have secondary, tertiary, right? We have the issue that we could undergo an SN1 because SN1 reactions proceed through that planar carbocation intermediate. The stereochemistry that might exist at the carbon atom bonded to the leaving group would be lost. So if you started with something that was enantiomerically pure here, and it undergoes a reaction here, now you have a mixture of stereoisomers. Additionally, you're going to generate a carbocation, so you always look for carbocation rearrangements, right? And so let's say that you wanted to synthesize this molecule, and so you're like, hey, I'll start out with this guy. Well, you're going to get a carbocation rearrangement. Now, not all carbocation rearrangements are bad. If you want to start out with this, that's great. You could use that, right? So it's all in what you're trying to synthesize, whether things are necessarily good or bad. So because HCl and HBr have some limitations, we need other ways to go from an alcohol functional group to an alkyl halide. And good choices for this include phosphorus tribromide or phosphorus trichloride. So phosphorus tribromide or phosphorus trichloride don't have really any of the disadvantages that arise from using HBr. These convert an alcohol to a alkyl halide under mild conditions. There's no elimination products. So you don't have to worry about some of your main product the yield being reduced because you have elimination of products. The conversion is stereospecific. So it does take place with an inversion of configuration. So if you start out with a wedge here, you're going to get a dash here. That means if it's R, it'll be S, or S then R, right? So there is a inversion that you're going to see, right? And here is my favorite, because these are tricky: no carbocation rearrangements, right? So it's not something that you really have to look for. So I particularly prefer these over just using a base, because I feel like there's a little bit more control here. Just a real brief aside, you're going to notice PBr3 here. One of the commercial uses of PBr3 is the synthesis of methohexatol, which is marketed as Brevital or Brevital, which is used as an anesthesia for surgery. So just kind of a fun aside of a practical application. I'm going to pause the screencast right then, so if there's a little bit of a break, you haven't missed anything. We just talked about the observations that we see, right? That we don't have any of the disadvantages that arise from using HBr. And these observations are explained by the mechanism. And so let's look at the mechanism here. So we're going to take this molecule here. And with our friendly alcohol, and we're trying to convert that to an alkyl halide, and we're going to use PBr3. Now the structure of PBr3 looks like this. Now all these bromines are very electronegative. They have lots of electrons on them, right? And so what we find is that this phosphorus right here is very electron poor, okay? And what we also know is that this alcohol here is very electron rich. So these electrons go and attack that phosphorus. When they do that, they bump off one of these bromine in an Sn2 reaction. Okay, and so they form Okay, now I want you to notice I am not changing anything on this side, right? CH3 stays the same. But I come over here and this OH stays there. The O, we have the H. It's got 2 electrons. And the thing that's different here is it's going to have a phosphorus with the 2 bromines. So when you're learning these mechanisms, really use these arrows to tell yourself where the new bonds are going to be, right? Look, this arrow here, these electrons are forming a bond here. Look over here, we formed a bond here. This bromine is gone. That means the phosphorus now only has 2 bromines. Now, that bromine, of course, is still floating around, right? And can act as a electron-rich nucleophile and be attracted to the electron-poor carbon next to the oxygen, okay, through another Sn2 reaction. So this guy comes up here, attacks here, and that goes off. And so we have another Sn2 reaction. And now you've made your product. Here, I want you to notice a few things. Notice that the phosphorus containing group here in step 2 resembles, like, has a protonated alcohol on it. And when we think about this, right, when it leaves, that's going to be, it's going to resemble a really stable, uncharged water molecule. So when this leaves, it's going to be really stable because there's no longer going to be a charge on this oxygen. Also, I want you to notice how the mechanism accounts for the stereospecificity here. This is a backside attack. So the bromine comes in from this side and it leaves the leaving group is on the other side. So that's the reason we have the flip in stereochemistry here, or the inversion is because it's a backside attack. Notice that we didn't generate any carbocations, and so you can't have a carbocation rearrangement. Now, I would love to say that this was like the best mechanism ever and there were no limitations, but there are some limitations here. So recall that nucleophilic substitution reactions generally do not occur when a leaving group is on an sp2 or an sp hybridized carbon. And the same is true for these reactions involving phosphorus trihalides. So when we come over here, right, these generally do not occur right, when the leaving group is on sp2 or sp hybridized carbons, okay? The conversion of an alcohol into an alkyl halide with PBr3 or PCl3 only occurs when the OH group is bonded to an sp3 carbon atom. So it only occurs when the leaving group is bonded to an sp3 carbon atom. Okay. So I want you to notice here a few things. In this equation, right, the leaving group is on an sp2 hybridized carbon, so the halide doesn't form. Also recall that steric hindrance is a problem in Sn2 reactions. So we have a tertiary carbon here and you get a really, really poor yield. So this can't really readily undergo Sn2 reactions. It can undergo an Sn1 reaction, but then we end up with a carbocation issue again. So the reaction of a tertiary alcohol with PBr3 or PCl3 generally gives a really poor yield. So let's do an example. Okay. Predict the products of this reaction and draw its complete detailed mechanism. And let's pay attention to stereochemistry. So we have our friendly reaction here, and we're starting out, and we need to say, okay, here's some questions you need to ask yourself when you are asked to predict the products of a reaction. You need to ask yourself, what functional groups are present in this molecule and which are susceptible to a reaction with PBr3, okay? Well, PBr3 targets that OH functional group. We have two OH functional groups here. We have one here, right, and one here, okay? And so we need to ask ourselves, are both of those valid functional groups that can react? The one on the right is on a secondary carbon here, and then the one on the left is attached to a tertiary carbon here. Now, because this mechanism proceeds through an Sn2 attack, the secondary carbon is going to be prone to the reaction, but the tertiary carbon's not because of steric hindrance. So we can identify that PBr is going to attack and really change and attack this alcohol group because of the secondary carbon. So then you need to ask yourself, what type of functional group is produced and how is the stereochemistry of the molecule affected? Well, we're going to end up with an alkyl bromide, right? And so what we know is that it'll undergo an SN2 reaction. And so that means there's going to be a reversal of the configuration. Now, if I were just asked to predict the products here, if I was not asked to do the mechanism, I would come here if this was a predict the product reaction, and I would say, okay, so that's what I know about this. So then the product I would expect would be and then this configuration is going to change. BR would be that guy. Okay. And so you are going to have some predict the product problems where you might have to predict the product. You might have to predict the reactant. So I would say I would give you this and this, and you would have to fill in this piece. So you'd have to ask yourself, what reagent would cause the alcohol to be replaced by the bromine? Or I might give you this piece and tell me and say, okay, what starting material would go here? And you would need to know that it's an alcohol, right? So there's a lot of different ways we can ask these questions. I could also just ask you to show me the mechanism, which we're also going to do. So we're going to come down here. We've got P, Br3, okay, and we're going to remember that phosphorus is really electron deficient, and so the OH acts as very electron rich, and it's going to come in here and it's going to attack that phosphorus. It's going to bump off a bromine through an SN2 reaction. You're going to come here and we leave everything the same that's not involved in the mechanism. All right. And then we don't change the stereochemistry yet. Now you can shorten this to PBr2, just like that. Don't forget you've got electrons on the oxygen and a positive charge, okay? And then we have this free bromine with a negative charge. That free bromine is going to come back in and attack that guy right here through an SN2 reaction and bump that guy off. And so then we come here and we say, okay, this is the same. That's the same. And then this configuration changes to a BR, right? And there's the mechanism. So hopefully this gives you a really good idea of the type of questions that I could ask to help to predict the products or predict the reagent or predict the starting material. Now, so far we've studied two functional group transformations that convert a poor alcohol leaving group into a good halide leaving group. In the next section, we're going to examine reactions that place a halide leaving group on a carbon that does not initially have a leaving group at all. So let's look at this guy over here. So for example, we've got 2-methyl, 1-phenylpropane, 1-one here, and it has no good leaving group, okay? But when the ketone is treated with Br2 under basic conditions, a good Br leaving group is placed on the alpha carbon. Now, let's talk about the alpha carbon here. We start talking about when we have a ketone, right? The alpha carbon is the carbon next to the ketone. That's considered the alpha carbon, and so that's an alpha hydrogen. This is the beta carbon, and that's the beta hydrogen, okay? So unlike the leaving groups that we talked about before, where alpha started on the carbon of the functional group, really, here for the ketones, alpha is the one next to it. That's what we start with. I know that's confusing. Please do not shoot the messenger. I did not develop this. I just get to deliver the message. But I did want to point out that that's a little inconsistency with how we talk about alpha and beta. So this is called a halogenation reaction, and the alpha hydrogen has been replaced by the bromine. These can take place at the alpha carbon of a ketone or an aldehyde with chlorine, bromine, or iodine under basic conditions. People generally don't like to mess with chlorine. It tends to explode. And so we've really stopped dealing with that at all. So let's look at this mechanism. So we're going to practice drawing a lot here, and so it's just good to practice drawing some of these compounds again. One of the ways that I learned my mechanisms when I was a student is I wrote them over and over and over again. I killed lots of trees with all the paper I used, but it's really the only way I could learn it. Okay, so let's look at this. In the very first step, the base deprotonates the alpha carbon. So you will notice if you look back, I cannot flip back or this will break up, but you'll notice that we have Br2 reacting in the presence of a base. So the base is going to come along, and it was sodium hydroxide, but we know sodium's a spectator ion, and it is going to remove the proton there. Okay, because it's a little, that proton on the alpha carbon is just a little acidic, and so it reacts with the base. Then these electrons go back onto the carbon here. Okay, and so that is a general proton transfer reaction. Now, one of the things to know is that it forms an enolate ion, and the enolate ion is resonance stabilized. Now, we can show the two resonance structures by using brackets. Your book does this. You can see, and I'm going to just use a circle because I'm lazy for benzene rings. You can too. Feel free to embrace that. We form this guy, which is shown here, but understand there's a resonance structure here. Right, and that makes that intermediate particularly stable. So when we show resonance structures in the middle of mechanisms, we use brackets, and we can use either resonance structure to continue on to the next part of the mechanism. You do not have to show the resonance structure unless you are going to use this guy right here, which is not one that you would use. So if I broke up there, I had to pause the screencast just briefly. You haven't missed anything. As I was saying, you don't have to show the resonance structure unless you are going to use this resonance structure in the next part of the mechanism. I like to show them to you so that you can see them. I obviously will not count off if you just put them in. So what happens here then is we bring in Br2. Br2 looks like this. Okay. And what happens is that the carbon with its negative charge here, and don't forget your charges, I forgot mine, don't be like me, is more nucleophilic, right? This is actually called an enolate ion. Okay. And so what happens here is these electrons come out and they attack this bromine. These electrons go onto the bromine here. And so when that occurs, we get the product there, right? where we've replaced a alpha hydrogen with a bromine. And so, of course, then this can go on and react in other mechanisms, right? So, like, for example, here, with that leaving group on the alpha carbon, subsequent reactions become feasible that we could not have done before if that leaving group hadn't been present. So, for example, we call this the alpha halogenated product. Can act as a substrate in a substitution or elimination reaction, right? So we've really opened up the doors for being able to use this. Now, maybe the burning question in your heart is, hey, Dr. Pierce, back on that mechanism, why would a nucleophile like that enolate anion attack a molecular halogen? Why does it attack that Br? Because that Br is pretty electronegative. What's going on there? Well, halogens like chlorine, bromine, and iodine can behave as substrates in Sn2 reactions in part because they are highly polarizable. So what do we mean by that? If you look, this is an isolated molecule of Br2 and it's nonpolar. But what happens is when an electron-rich species like the enolate anion comes up close to it, the electrons on the halogen molecule are really easily repelled. And so you generate an induced dipole. So basically these electrons come up, the electrons that are on this bromine are like, I don't want anything to do with you. And they run over here and it causes this end to become partially positive. Well, if that's partially positive and that's negative, these go over there and attack. So the halogen atom that's near the nucleophile becomes electron poor. And so as a result, a bond can form and we draw an arrow. That's wild. This is wild to me. It's just so exciting, right? Now, if we look back at the alpha halogenation mechanism that we saw in equation 1035 or equation 1036, notice that the alpha carbon on the enolate anion is bonded to 3 groups, where it's bonded to 4 groups in the halogenated product. So that means if the alpha carbon becomes a chiral center when it gains the halogen atom, that's step 2, then both the R and S configurations will be produced. So what this means is, right, if we undergo a bromination, notice that you can get both the R and the S, right? Because there's an intermediate there where you only have 3 groups and it kind of goes back to being planar. Okay, so you get a mixture of stereoisomers here. Now, a fun thing about the halogenation reaction is that, and I'm sure you have already noticed this because you're a savvy student, you have noticed that we have only shown ketones that have a single alpha hydrogen. Well, if you have a ketone that contains more alpha hydrogens, you can replace all the alpha hydrogens with bromine, okay? So under basic conditions, which is what we have, polyhalogenation often occurs, and poly is just that prefix that means many. And so what you notice here is you have 2 alpha hydrogens here. There aren't any here, but there are 2 here, and so you can get 2 bromines here. Alpha halogenation does not stop after the single substitution because the second halogenation is faster than the first halogenation. The second alpha halogenation is faster because the addition of the first halogen makes the remaining alpha hydrogens more acidic. So this can keep going. If you have a molecule where you had alpha hydrogens here, it would also halogenate those as well. Let's look at this mechanism, right? So what we see happening here is we have an OH here, and it's a nucleophile. It's going to come in and it's going to steal this acidic alpha hydrogen. When it does that, these electrons go here and you have your enolate anion. Now, notice here's your resonance structure. You don't have to show this part because this isn't going on to work and to do anything in the mechanism, but the book and me both like to show it just so you know that this is really very stabilized with this enolate anion. These electrons come here, and because that's very electron rich, and they induce a dipole, and this bromine becomes electron poor. Then these electrons go here onto the bromine. So what happens is we've got this halogen now, it's withdrawing electron density, and it increases the acidity of this hydrogen here. So the hydroxide ion comes right in again, and it goes, and those electrons go there, right? We end up with an enolate anion. These electrons, again, electron rich to electron poor, and we get the polyhalogenation. So it's just exactly like the other mechanism we saw. We just see the steps a second time, okay? And then if you have more halogenations, it's just the same thing over and over and over again. Now, if polyhalogenation is not desired, if that's something you don't want, then we can change the conditions where and how the reaction's carried out to control that. Because under acidic conditions, you only have a single halogenation that takes place. So a really good example of this is 1040 here. This, when it's shown like this, is acetic acid. Right? And so that's a shorthand. I've said that really confidently and then I scared myself. That's acetic acid. That's a shorthand for acetic acid. Sometimes they'll also show the CH3 COH like that, but also remember it can be shown like this or like this or HOAC. Okay, so lots of different ways we can show acetic acid. Those are basically all synonyms for each other, so don't panic over that. And so this is in acidic conditions. A negatively charged enolate ion can't exist in any substantial concentration because it's really strongly basic. But the alpha carbon can still become electron rich by an alpha catalyzed ketyl-enol tautomerization. And so let's look at that mechanism. So different mechanism here. All right. So all right. So we've got our acetic acid. Now, when I'm messing with alpha hydrogens, particularly, I like to go ahead and draw those suckers in just so I know what I'm working with. So I'm going to draw one in. There are two there. You can draw two if that makes you happy, but I like to go ahead and draw one in just to remind myself this is what we're doing. Okay. So the first step is a proton transfer where this alcohol is going to come out and grab that proton and the electrons go back on the acetic acid there. So it's just a generic proton transfer. Okay, and we follow our arrows and we say, okay, we've added a hydrogen there. We still have 2 electrons, but now we have a positive charge. We also have the deprotonated acetic acid running around. That deprotonated acetic acid is going to come in and still that proton to go back and make protonated acetic acid. When it does that, these electrons come here to form a double bond, and these electrons bump up here to remove that positive charge. And so what we end up in then is this molecule. Now, I'm going to put brackets around it, okay? This is an enol molecule. An enol is when you have a double bond next to an OH. This was one of our mechanisms that we talked about in Chapter 7. What can happen is these have resonance and can form a ketose structure. So I want to show you that resonance, but I want to use a different color. So I'm going to use the green here, where this can come down here and that can go there. Okay, and so that's the resonance. I'm showing the mechanism arrows in red and the resonance there in green. What happens now, right, is this is one of the examples where we are going to use the keto form here. So this is the keto form to go through the next step of the mechanism. So in the next step of the mechanism, it's an Sn2. Sorry, I forgot to label that as another proton transfer. This is an Sn2. We are going to do this with chlorine. All right. With chlorine, these electrons come up, right? And they're going to attack that chlorine. Those electrons go there, right? Just like with the Br2, it's just we're using Cl2 here. When that occurs, we end up with this guy. Okay, and we have another proton transfer that occurs because we have some of the conjugate base of the acid running around. And so this comes here, it steals that proton, those electrons go right there, right? And then we end up with that guy. And this will not happen again because what happens here is you end up with some electron withdrawing effects from this chlorine here, and it destabilizes any nearby positive charges. So you can't protonate this alcohol group, this carbonyl group again, right? Because we get electron withdrawing effects if it's for the chlorine, right? So what I'm saying here is if for the first step, we were to come here again, and the protonation here, that is so unstable because the chlorine withdraws electron density. And so it becomes so unstable, it's just not feasible. And so it doesn't happen. So that's what we're talking about there. All right, so this concludes our third screencast. We've really been focusing on some transformations of functional groups to increase your synthetic toolbox so that we can do multi-step synthesis.